Hey guys, today we're going to be learning lesson 3.1, which is the nature of exponential growth. The example that we're going to look at first is how to model exponential growth. Right? So a type of bacteria grows that it triples in number every day. On the day that Roger begins observing the bacteria, a sample has a population of 100. Okay, so it triples every day, and then the first day that he looked at it, it had a population of 100. So the first question is find the population after each of the first 4 days. Okay, so first I'm just gonna set it up in like a table so it's easier to understand. So day population. So on day 0, okay, he saw that there was 100 bacteria, right? On day 1, it is 100 times 3 because it triples. So I get 300. On day 2, I get 300 times 3, which is 900. Day 3, I get 900 multiplied by 3, which is 2700. And finally on day 4, I get 2700 multiplied by 3, which is 8100. So the second part asking to write an equation to model this growth. Okay. To better explain this, let's take a look at the above table again. Okay, we can notice that here is pretty much just population of 100. On the second day, you're taking 100 multiplying by 3. Okay, and then here we have 300 multiplied by 3. But for day 2, you can think of it as 100 multiplied by 3 to the power of 2. So it's like 100 multiplied by 9. So I get 900. So I'll just rewrite this. So it's kind of confusing. So 0, 1, 2, 3, 4. Here I have 100. Here I have 100 multiplied by 3. Here I have 100 multiplied by 3 to the power of 2. Okay, so here I'll have 300. Here I'll have 900. 100 multiplied by 3 to the power of 3 is 2700. And 100 multiplied by 3 to the power of 4 is equal to 8100. Okay, so if I was to devise an equation to represent this growth, it would be, say, the population for the number of days, n, is equal to 100 multiplied by 3 to the power of n, number of days. Graph the relation. Is it a function? Explain why or why not. Alright, so let's just do this. I'll show you on the graphing calculator. Of course, this one's broken. Okay, so the equation was 100 multiplied by 3 to the power of n. So that's x. And that's the graph that I have right there. Okay. So since like the days can't be below 0, like can't be negative, because we start times 0, right? So times 0, let's zoom up a bit here. You see that it starts at 100 right about there. Okay. Then after that, it just increases pretty quickly after that. It's hard to kind of gauge the scale, but pretty much I'll show you here. The quick sketch. It looks like that. Over here, start at 100. So is it a function? Yes. Because the graph has only one y value for every x value. Okay, another way to think of it as the vertical line test, right? You can only pass through the vertical line once, no matter where you go. Okay, assuming this trend continues, predict the population after 2 weeks. So 2 weeks, your n is going to be equal to 14 days. Okay, so if I plug it into the equation, I have 100 multiplied by 3 to the power of 14. It equals to, let's see, 4, 7, 8, 2, 9, 6, 9, 0, 0. Okay, the population is 978,296,900. Describe the pattern of final differences for this relationship. Okay, so for that we got to go back to that chart again. So day population. So we have 0, 1, 2, 3, 4, 100, 300, 900, 2700, 8100. Probably shouldn't have wrote this that big, but so first final differences here is 200. Then we have 600. We have 1800. Then we have 5400. Okay, the way I got that is I took 300, subtract 100, I get 200. 900, subtract 300, I get 600, and so on and so on. I do the same thing here. 600 minus 200 is 400. 1800 minus 600 is 1200. And finally, 5400 minus 1800 is 3600. Okay, so as you can see the pattern, if we kept on going on and on, like say 1200 minus 400, we get 800. 3600 minus 400, we get 2400. So the trend is, even for the first column, okay, it triples. 100 to 300, 300 is 900, 900, so on. It keeps on tripling. For the first finite differences, 200 to 600 triples, 600 to 1800 triples, and so on. And then even on the third and fourth, they keep on tripling. Okay, so the pattern for finite differences are always triple. Well, actually, probably a better way to say it's successive. Successive finite differences are always tripled. Okay, and it's only tripled because in this specific example, the bacterial population triples after every day. But if it said it doubled, then obviously the finite differences would be doubled. If the population halved with every day, then the finite differences is always halved, so on. Okay. So just a quick summary of what we learned in the first example is that exponential growth functions have these properties. As the independent variable increases by a constant amount, the dependent variable increases by a common factor. Okay, and in that bacterial example, the common factor was 3. Okay, so you multiply it by 3 after every time. The graph increases at an increasing rate, and that's straightforward. And finally, the finite differences exhibit a repeating pattern. The ratio of successive finite differences is constant. Okay. Alright, and now we're gonna just do a quick little blurb on the zero exponent. So pretty much talking about what it means to apply any number to the exponent 0. So in our example, going back to the bacterial example, right? Day population. If you remember, it was 0, 1, 2, 3, 4. It was 100, 100 multiplied by 3, 100 multiplied by 3 to the power 2, 100 multiplied by 3 to the power 3, 100 multiplied by 3 to the power 4. So here you can think of this as power of 1, okay, so it's 100 times 3 by itself. Then 100 times 3 to the power 2, 900, and so on. But as you can see, at day 0, you can think of it as multiplying by 3 to the power of 0. Okay, and if you punch into your calculator, if you take 3 to the power of 0, it will equal to 1. Okay, so this is actually just equal to 100. So applying anything to the zero exponent just takes it down to number 1. So you can think of this as a to the power of 0 is equal to 1 as a general rule, where a is any integer that isn't 0. Okay, so as a summary, any base to the exponent 0 equals to 1. So I'll just rewrite this here. Is equal to 1 for b is in the domain of any real number, okay, meaning any decimals or fractions or whatever, and where b can't be equal to 0. Okay, that's it. Thanks.